Okay, welcome back, section 4-2, to the calc lesson. So pretty much this section, derivative of product of two functions, this skill is lovingly referred to as the product rule. Now, just a quick refresher, a product is a multiplication. So technically we're saying if we have a function that can be split up into the multiplication of two functions. Oops, that should be an x. Then this trick will work. Let's see. Now, I'm going to go ahead and just lay out the rule itself. Then we'll look at some examples. And after that, we might take a look at where it comes from. So, the rule says if we have a function that can be split into two functions, we can pretty easily find the derivative. Now, instead of g of x, h of x, I'm going to split it up into a u component and a v component. Just make it easier on the eyes. So if this is our function, a function of two components multiplied together, then the derivative of this function is the derivative of the first component times the second component plus the first component times the derivative of the second component. So it's pretty simple finding the derivative using the product rule. Okay, it's not a hard task. So let's take a look. So the first example in the book says if we have a function y equals x to the fourth cosine 6x, and it says find dy dx, the derivative. So let me scroll down here. First of all, I have to be able to identify my two components. So this one's not too hard. My first component is x to the fourth. My second component is cosine 6x. So I find the derivative of the individual components. I get 4x to the 3. And v prime is negative 6 sine 6x. Now, what I did was chain rule in my head. Derivative of the inside times derivative of the outside. So, uv, u prime, v prime. Now all I have to do is u prime v, so 4x to the 3 cosine 6x plus u v prime. Oops, sorry, there's a plus there. That should be a times. Sorry about that. u v prime. Alright, so I have 4x to the 3, which is u prime, cosine 6x, which is v. Now it's u v prime, so minus 6 x to the fourth. Just trying to put it in order so I can save myself a simplification step. Sine 6x, and that's it. So separate it into two components, find the derivatives of each respective component, and then u prime v plus u v prime. So that's it. Let's take a look at another. So example 2. From the book, it says our function is y equals 3x minus 8 to the 7th, 4x plus 9 to the 5th, find y prime. Okay, so this one's not too hard to figure out my individual components. U equals 3x minus 8 to the 7th. V equals 4x plus 9 to the 5th. Now technically both of these are chain rule. Derivative of the inside, derivative of the outside. But since we've been doing chain rule for a while, I'm going to go ahead and skip that and do it in my head. Derivative of the inside is 3 times the exponent, so 21. Then 3x minus 8, 7 minus 1 is 6. V prime, derivative of the inside is 4 times the exponent, so 20. then 4x plus 9, and 5 minus 1 is 4. Okay, so I have my uv, my u prime, and v prime. Now let's go ahead and put it together. So y prime equals u prime v. So this and this, 21, 3x minus 8, whoops, 6, 4x plus 9 to the 5th, and then uv prime plus 20 on the front, 3x minus 8 to the 7th, 4x plus 9 to the 4th. And that's it. Now, technically you could simplify this somewhat, but it's good what it is right now. So, you can also see that the derivative starts getting pretty long when it's uv prime and u prime v adding together. Now, if we have to do two product rules in a row, that gets even more ridiculous. All right. Now, moving on a little bit. What if we have a third component of our function? Okay, so let's talk about a third component. So in this case, what I'm talking about is what if I have y equals u, v, w? Three components multiplied together. Now, the trick works for this as well, and it just means things get really long. So y prime equals u prime vw plus u v prime w plus u v w prime. So there is a proof for this that I'm not going to worry about right now. This is one of those tricks that for now, what's important is you know how to use it, not necessarily how it works. Okay? Know that it exists, know how to use it, and then in the future we can talk about why it works. So let's see it applied to one of the homework problems from this section. Let's see. We'll take a look at number 19 from this section. So our function z equals x to the 3, parentheses, 5x minus 2 to the 4th, sine 6x. So, three components. My u is x to the 3, my v is 5x minus 2 to the 4, and my w is sine 6x. Find the three respective derivatives. U prime equals 3x squared. V prime equals, derivative of the inside is 5 times 4 is 20. Then parentheses, 5x minus 2. And then 4 minus 1 is 3. And W prime equals, let's see, derivative of the inside, 6, and outside, cosine 6x. Now, I just got to turn this into a nice long derivative. So y prime, u prime vw, so 3x squared, 5x minus 2 to the 4, sine 6x, plus u v prime w, so u v prime w, 20x to the 3, 5x minus 2 to the 3, sine 6x, and I'm going to continue it underneath since I ran out of room, so plus UVW prime, UVW prime, so a 6 on the front, x to the 3, 5x minus 2 to the 4, and cosine 6x, and that's it. So technically we could have done two product rules in a row, but this trick is much, much nicer and much more straight to the point and concise. Now, since we now know the product rule, we can apply it to our knowledge of the chain rule, which we're also going to learn the quotient rule, and it's just yet another tool to include in your bag of tricks for differentiating large functions.